At some point, almost everyone looks up at the night sky and asks the same quiet question, is this all there is? Surrounded by billions of stars, scattered across a universe nearly 14 billion years old, Earth feels both special and suspiciously ordinary. Science fiction often answers this question with dramatic certainty. Aliens everywhere, civilizations around every star, but real science approaches it far more carefully. Instead of asking where life is, it first asks a deeper question. What makes life possible at all? That shift is crucial. The universe does not owe us life, intelligence, or meaning. Life is not guaranteed by size or age alone. Contrast the cinematic expectation of crowded galaxies with the scientific reality that life is a process, not a destination. It does not simply appear because a planet exists. It emerges only when specific conditions align, and those conditions are governed by physics, chemistry, and time. For much of human history, life was assumed to be unique to Earth. This was not arrogance, but lack of information. Earth was the only example we had. As telescopes improved and space exploration began, that assumption weakened. We discovered planets around other stars, extreme life thriving in Earth's harshest environments, and chemical complexity scattered throughout space. Each discovery chipped away at the idea that life is fragile coincidence, replacing it with something more intriguing, possibility constrained by rules. The search for life elsewhere is often misunderstood as a hunt for beings that look or think like us. In reality, it is a search for environments where complexity can persist. Life does not begin with intelligence or technology. It begins with stability. It requires energy that flows without destroying structure, matter that can assemble and reassemble, and conditions that last long enough for complexity to grow. Contrast this slow, patient process with the instant creation myths we instinctively favor, and the universe begins to feel less magical but more profound. This perspective reframes Earth itself. Our planet is not simply lucky, it is informative. Earth shows us that life arises where certain thresholds are crossed, where chemistry becomes rich, where energy is available but not overwhelming, and where change happens slowly enough for adaptation to keep pace. Earth is not the template for life everywhere, but it is the proof that life is possible under natural laws. There is also a psychological layer to this question. Asking what makes life possible forces us to confront uncertainty. It challenges the idea that humans are central, inevitable, or special by design. Contrast that discomfort with the excitement of discovery, and you see why the question persists across cultures and generations. It is not just about aliens. It is about understanding whether life is rare accident or natural outcome. Importantly, science does not begin by assuming life must resemble us. It begins by identifying constraints. What kinds of universes allow complexity? What kinds of stars live long enough? What kinds of planets maintain stable environments? By asking these questions, the search for life becomes broader, more rigorous, and more honest. It replaces wishful thinking with evidence-driven curiosity. This section sets the foundation for everything that follows. Before we can imagine life elsewhere, we must understand the conditions that make life possible anywhere. Not by appealing to mystery, but by tracing the quiet, consistent rules that govern matter and energy across the cosmos. Once those rules are clear, the universe transforms. It stops feeling empty and starts feeling conditional. And in those conditions lies the real story of life, one written not just on Earth, but potentially across the stars. Life does not begin with biology. Long before cells, DNA, or ecosystems, life depends on physics. If the universe were only slightly different in its fundamental rules, complexity would never arise at all. No stars, no planets, no chemistry, just chaos or emptiness. The fact that life is possible anywhere begins with a narrow set of physical conditions that allow structure to exist in the first place. At the most basic level, the universe is governed by a small number of fundamental forces. Gravity shapes large-scale structure, pulling matter together into stars and galaxies. Electromagnetism governs chemistry, binding atoms into molecules. The strong nuclear force holds atomic nuclei together, while the weak force enables radioactive decay and energy transfer in stars. Contrast a universe where these forces are balanced with one where they are slightly altered, and the difference becomes dramatic. Too much gravity, and the universe collapses too quickly. Too little, and matter never clumps at all. The values of these forces matter just as much as their existence. If electromagnetism were slightly stronger, atoms would not bond easily. If it were weaker, complex molecules would fall apart. Life depends on chemistry that is stable but flexible, and that balance is surprisingly delicate. Contrast the apparent robustness of the universe with a narrow window that allows complexity, and life begins to feel less inevitable and more conditional. Stars play a central role in this story. Life requires a long-lived, stable energy source, and stars provide exactly that. They convert mass into energy through nuclear fusion, producing light and heat over billions of years. Short-lived stars burn too fast. Violent stars fluctuate too wildly. Only certain types of stars provide the steady conditions necessary for planets to maintain long-term stability. The universe contains many stars, but not all are equally suitable for supporting life-bearing environments. Time itself is another critical factor. The universe had to age enough for heavy elements to form. Early after the Big Bang, the cosmos contained mostly hydrogen and helium. Elements like carbon, oxygen, nitrogen, and iron were forged later inside stars and scattered through supernova explosions. Without this chemical enrichment, planets like Earth could not exist. Contrast the early universe with the present one, and it becomes clear that life is not just about where you are, but when you are. Space also matters. Galaxies provide environments where stars and planets can form repeatedly, recycling material across generations. Too close to a galactic center, radiation and gravitational chaos dominate. Too far out, and heavy elements become scarce. Life-friendly regions exist in a kind of cosmic middle ground. This balance is not designed, it emerges naturally from physical laws operating over immense scales. Even the structure of space-time itself plays a role. The expansion rate of the universe influences how matter clumps and how long stars can shine. If expansion were too fast, matter would disperse before structure formed. Too slow, and everything would collapse prematurely. Contrast the universe we observe with these alternatives, and it becomes clear that life is possible only because multiple conditions align simultaneously. None of this implies intention or purpose. Physics does not aim for life. It simply allows it under specific circumstances. Life is not written into the laws of the universe, but it is permitted by them. That distinction is important. It reframes life not as a cosmic miracle that defies nature, but as a rare and remarkable outcome of consistent rules applied over vast time and space. Understanding these physical foundations changes how we think about life elsewhere. Instead of searching blindly for familiar shapes or signals, science looks for these enabling conditions. Where physics allows complexity to persist, life becomes possible. And once the physical rules are in place, chemistry takes over, building the next layer of the story. Once the physical rules allow structure to exist, life still does not appear automatically. Physics sets the stage, but chemistry writes the script. Life, at its core, is organized chemistry matter that can store information, process energy, and replicate with variation. To understand what makes life possible anywhere in the universe, we must look closely at the chemical conditions that allow complexity to grow instead of collapsing into disorder. One element dominates this discussion: carbon. Carbon is not special because it is rare, but because it is versatile. It can form stable bonds with many other elements, including itself, creating long chains, rings, and complex three-dimensional structures. Contrast this with elements that form only simple or fragile bonds, and carbon's power becomes obvious. It allows molecules to be both stable enough to persist and flexible enough to change, which is exactly what life requires. Carbon alone is not enough. Life also depends on a medium that enables chemical reactions to occur efficiently. On Earth, that medium is water. Water is often treated as synonymous with life, but its importance comes from specific properties. It is an excellent solvent, allowing molecules to move and interact. It remains liquid across a wide temperature range. It moderates heat, stabilizing environments against extreme fluctuations. Contrast water with other liquids, and it becomes clear why it is so effective at supporting complex chemistry. This does not mean life must always use water. It means life needs something that plays a similar role. Scientists consider alternatives like liquid methane or ammonia in colder environments, but these come with trade-offs. Their chemistry is slower or less flexible. The contrast highlights an important idea. Life is constrained, but not necessarily identical everywhere. The universe may host forms of life, built on different chemical foundations, provided those foundations allow information, energy flow, and self-organization. Energy is the third essential ingredient. Life requires a controlled energy source. Too little energy, and chemical reactions stall. Too much, and complex molecules break apart. On Earth, sunlight drives photosynthesis, while chemical energy powers life deep underground or beneath oceans. Contrast explosive energy sources with steady ones, and the pattern is clear. Life thrives where energy flows gently enough to be harnessed, not where it overwhelms structure. Time is just as critical as ingredients. Chemical complexity does not emerge instantly. Simple molecules must interact repeatedly, forming more complex arrangements through countless cycles. This requires environments that remain stable for long periods. A planet that freezes, boils, or shatters frequently does not give chemistry enough time to experiment. Contrast a chaotic environment with a stable one, and you see why longevity matters as much as composition. Another misconception is that life requires perfection. In reality, chemistry is messy. Reactions fail, Molecules break, errors occur constantly. Life does not eliminate these flaws, it exploits them. Variation enables adaptation. Imperfection drives evolution. Contrast the assumption that life demands precise conditions with the reality that it emerges from trial, error, and resilience, and life appears less fragile than imagined. Importantly, many of life's ingredients are found throughout the universe. Organic molecules exist in interstellar clouds. Water ice coats distant moons. Carbon compounds form naturally in space. This does not mean life is everywhere, but it does mean the building blocks are not rare. What is rare is the sustained combination of ingredients, energy, and time. Chemistry bridges the gap between physics and biology. It transforms abstract laws into tangible complexity. Once the right chemical systems emerge, life becomes possible, not guaranteed, but allowed, and that realization expands the search dramatically. Life is no longer confined to Earth-like planets alone, but to any environment where chemistry can remain dynamic, stable, and creative long enough to cross the threshold into biology. With this chemical foundation in place, the next question becomes obvious. Where in the universe do these conditions actually exist? And how many environments might quietly meet the requirements for life, even if they look nothing like Earth from afar? For a long time, the search for life focused almost entirely on planets that look like Earth. Rocky worlds orbiting sun like stars, sitting at just the right distance for liquid water on the surface. This idea, known as the habitable zone, shaped decades of thinking. But as our understanding deepened, that narrow view began to fracture. Life, it turns out, may not be as picky about its surroundings as we once assumed. The first crack in the Earth-only mindset came from our own planet. Life thrives in environments once thought impossible. All deep beneath the ocean floor, organisms survive without sunlight, powered by chemical energy from Earth's interior. In acidic lakes, frozen tundra, and radioactive waste sites, life persists by adapting to extremes. Contrast the comfortable surface world humans inhabit with these harsh environments, and it becomes clear that habitability is broader than intuition suggests. This realization transformed how scientists look at other worlds. Moons, once dismissed as frozen and lifeless, suddenly became compelling targets. Beneath the icy crust of Europa and Enceladus lie vast subsurface oceans, kept liquid by gravitational heating rather than sunlight. These environments are dark, cold, and alien, yet they contain water, energy, and chemical complexity. Contrast the classic image of a life-friendly planet with these hidden oceans, and the universe appears far more inventive. Mars offers another lesson in shifting expectations. Once wetter and warmer, it may have hosted environments suitable for microbial life billions of years ago. Even today, traces of water and chemical activity remain. Mars reminds us that habitability is not static. Planets evolve, conditions change. Life may arise, persist briefly, or retreat underground as environments shift. Contrast the idea of permanent habitability with this dynamic reality, and the search for life becomes a study of planetary history, not just present conditions. Beyond our solar system, thousands of exoplanets reveal staggering diversity. Super-Earths, mini-Neptunes, tidally locked worlds, and planets orbiting red dwarf stars challenge familiar assumptions. Some may have thick atmospheres that redistribute heat. Others may experience constant stellar flares, yet retain subsurface refuges. Contrast the simplicity of the habitable zone concept with this diversity, and it becomes clear that life-supporting environments may exist in forms we are only beginning to imagine. Energy sources further expand the picture. Sunlight is not the only driver of life. Chemical gradients, geothermal heat, and tidal forces can sustain ecosystems. On Earth, entire communities exist without ever seeing the sun. This suggests that life elsewhere could thrive in perpetual darkness, far from stars, as long as energy flows steadily. Contrast star-centered thinking with energy-centered thinking, and the universe opens up dramatically. Importantly, habitability does not guarantee life, it only permits it. Many environments may meet all known criteria and remain lifeless. Chance, timing, and history still matter. But the key insight is this: life is not restricted to planets that resemble Earth's surface today. It is constrained by processes, not appearances. By expanding our definition of habitable environments, we also expand our understanding of life itself. Life becomes less of a fragile accident, clinging to a single world, and more of a resilient process that can take root wherever conditions allow. This reframing does not make the universe crowded with life by default, but it makes it far less empty than once imagined. With this broader view, the final question naturally emerges. If life is permitted by physics, enabled by chemistry, and supported by diverse environments, what would it mean to discover that life has actually taken hold elsewhere? And how would that knowledge reshape our understanding of ourselves? If we were to discover life elsewhere in the universe, the impact would extend far beyond science. It would quietly but profoundly reshape how we understand ourselves, our planet, and our place in the cosmos. Life beyond Earth would not simply answer a question, it would reframe the story we tell about existence itself. Contrast the long-held assumption of cosmic isolation with the possibility of shared biology, and the meaning of life shifts from rare exception to natural outcome. The most important change would be conceptual. For centuries, humans have wondered whether life is a miraculous anomaly or a common consequence of physics and chemistry. Finding life elsewhere would strongly suggest the latter. It would imply that life emerges when conditions allow, not because of special circumstances unique to Earth. This would not diminish the value of life here, it would contextualize it. Earth would become one example, not the exception. Such a discovery would also transform biology. Life elsewhere, even if microbial, would reveal whether evolution follows universal patterns or depends heavily on chance. Does life always rely on similar molecules? Does it organize information in familiar ways? Or does it solve the problem of survival differently? Contrast Earth's biology with an independent origin of life, and suddenly biology becomes a cosmic science, not just a terrestrial one. There would also be a psychological shift. Humans have long defined themselves by separation from animals, from nature, from the universe itself. Evidence of life elsewhere would soften those boundaries. It would suggest continuity rather than isolation. We would no longer be life surrounded by emptiness, but part of a broader living cosmos. This realization would not answer every philosophical question, but it would alter their framing. Importantly, discovering life elsewhere would not automatically mean discovering intelligence. Most life on Earth has been microbial for the majority of its history. Intelligent, technological civilizations may be rare, even if simple life is common. Contrast popular expectations of advanced aliens with the scientific likelihood of simple organisms, and the discovery remains profound without being dramatic. A single cell beyond Earth would be enough to change everything. This perspective also tempers fear. Contact with distant life does not imply invasion or threat. Space is vast, time is long. Life elsewhere would most likely be distant, ancient, or fundamentally incompatible with us. The real significance would be informational, not confrontational. It would tell us something about how the universe behaves when complexity is allowed to unfold. There is also humility in this possibility. Life elsewhere would remind us that the universe is not built around human concerns, meaning is not assigned from outside, it is constructed from understanding. Knowing that life can arise in many places does not make human experience smaller. It makes it more connected. It situates us within a larger narrative of matter becoming aware of itself under certain conditions. Even the absence of detected life would be meaningful. If the universe permits life, but rarely produces it, that rarity would demand explanation. It would sharpen questions about origin, timing, and fragility. Either outcome abundance or scarcity teaches us something fundamental about reality. Ultimately, the search for life elsewhere is not just about finding neighbors. It is about understanding the relationship between laws of nature and the emergence of complexity. Life is not separate from the universe. It is something the universe does when conditions align. That insight alone changes how we see ourselves. If life exists elsewhere, we are participants in a broader process. If it does not, then the responsibility to preserve and understand life here becomes even greater. In both cases, the question of what makes life possible anywhere leads back to us, urging curiosity, care, and perspective in a universe that is vast, consistent, and quietly capable of producing wonder.